Everyone, how's it going? So we're looking at doing this lab today. This is the fourth lab of the year, and we were determining g. Okay, that's the acceleration due to gravity. So any object in free fall. So I had a lab plan, but really what we ended up looking at was a video of my data. Okay, so of me dropping the object. That was the same video we used in class 12. If you're wondering where that is, the class 12 video, you can check that out on the channel. Hit the subscribe button. All right. So we calculated acceleration using an equation. That equation was d equals v initial times time plus 1/2 a t squared. Now, whenever we drop an object, the initial velocity, that's what VI stands for, the initial velocity is going to be 0 whenever anything's dropped. It's not always going to be 0, but if it's dropped, it's going to be 0. All right, so in this case, d is distance or displacement. We're just falling down, so they're the same thing here. V initial is the initial velocity. All right, t is time. And a is acceleration. So you were taking data very similar to what you did in class 12, and you were filling out all of the times first to go all of these different displacements. And then we're using those times to find acceleration. How do we do that? Well, let's do a quick example, just one. So let's say the first time to fall 0.2 meters, it was 0.19 seconds. That was a number that a good number of people had. So let's write out our equation here. D equals V initial times time plus 1/2 a t squared. So first things first, since we're dropping the ball, the initial velocity is 0. So let's do that part first. D equals 0 meters per second times t. Any number times 0 is 0, so that t doesn't really matter, plus 1/2 a t squared. So let's see, d, we'll plug that in, 0.2 meters, 1/2. A is going to be, let's see, oh, that's our unknown. We're solving for a. And then t is going to be 0.19 seconds, and only that number is squared. So to get a alone, first thing we'll do is multiply both sides by 2 to get rid of this 1/2. So we have 0.4 meters equals a, and let's quickly square 0.19. 0.19 times 0.19, we get 0.0361 seconds. The seconds get squared as well, but that's just a unit. It's just along for the ride. Mathematically, it doesn't affect this number over here. Now we need to divide both sides by 0.0361. So let's do that real quick. 0.4 divided by 0.0361. We get 11.08 meters per second squared. That's your acceleration there. So you put that number right here. You actually don't need to put the units on because they're at the top here, so you can just leave it like that. So you're going to do all these accelerations. They should all come out to be ballpark the same number, and then you put the average down here of them. Now the accepted value, though most people are getting a number higher than this, the accepted value on your equation sheet is 9.8 meters per second squared. That's the acceleration due to gravity for any falling object. That is on your reference table, and I would highly recommend you go look at that right now and figure out where that is. Okay, it's on the top of your reference table on the first page. We call that little g, acceleration due to gravity on Earth. Now what we did was we answered a question. The question was, how does the mass of an object affect its acceleration toward Earth? So the question is either more mass, more acceleration, less mass, more acceleration, or it doesn't matter. Who knows? I'm going to do what's intuitive. I'm just going to write a claim here. More mass equals more acceleration. I don't know if that's true or not. So we did two things in class. I'm not going to write it down, but I will kind of, actually, I am going to write it down, let's say. So we did two investigations. The first one was we watched this video here. In this video, they dropped a bowling ball into feathers, and we found that when there was no air resistance, when there's no air present, they accelerated toward the ground at the exact same rate. We also did an experiment in class. That experiment was drop a heavy ball and a light ball, one made of paper, at the same time see which hits ground first. All right, so after we did that experiment, we saw that the heavy and the light balls hit the ground at the same time. Okay, so our reasoning, how do your results of your investigation support or refute your claim? The mass did not affect the acceleration. Now, actually, maybe I'll put that down in my conclusion. Let's kind of reword this for just a moment. So we'll say, since heavy and light hit ground at same time, mass does not affect acceleration. If it did, if the more massive one accelerated faster, it would hit the ground first, but it did not. So in conclusion, mass does not affect acceleration due to gravity. All right? That's a really important concept. All right, so let's do some problems real quick. So the first one here, how long would it take a penny dropped off the Empire State Building, which is 381 meters high, to hit the ground? So we have some givens here, more than you think. So the obvious given is that D equals 381 meters. But we actually have two more. First, it's falling and it's near Earth's surface. So the acceleration is going to be 9.8 meters per second squared. We just got to get in that habit of kind of understanding that. Also, we know that the penny is dropped. That tells us that the initial velocity is going to be 0 meters per second. All right? And we're looking for what? We're looking for time. So writing down our givens kind of tells us which equation to use. We only have one right now, but in the future, we're going to have a lot of equations. So get in the habit of writing down your givens and unknowns. So D equals V initial times time plus 1/2 A T squared. So let's just plug everything in. D is going to be 381 meters. Make sure you put in the units the first time you plug it in. Initial velocity is 0 meters per second times T. Okay, so, well, that just becomes 0, right? Plus 1/2, 9.8 meters per second squared times T squared. We're solving for T. All right, so just to clean this up a little bit, 381 equals 1/2 of 9.8 is 4.9 T squared. Divide both sides by 4.9, we get something like 77.7, I think, equals T squared. Square root of both sides, and we get T equals 8.8 seconds. That's just algebra there. Really, the physics is understanding how to set up the problem, the givens, the unknowns. Everything else is just algebra after that. All right, so this method can be used to measure the height of a building. Right, so if it takes 4.5 seconds, so there is our time, for a penny to hit the ground when dropped, so we know dropped, so the initial velocity is going to be 0. From a building, how tall is the building? So we're looking for distance, how far it fell, and we know the acceleration is going to be 9.8 meters per second squared. That's the accepted value. Don't use your value from lab. It's not really going to be that accurate. All right, so let's see here. D equals V initial times time plus 1/2 AT squared. All right, D, let's see. D is our unknown. V initial is going to be 0 meters per second times T. So that whole thing becomes 0 plus 1/2. A is 9.8 meters per second squared. And T squared is going to be 4.5 seconds. Okay, only that number is squared. When you throw that in your calculator just like that, only the 4.5 is squared, you get about 99.2, I think, meters. And last but not least, G is not 9.8 meters per second squared on Mars. It's different on every planet. And if you get really far from Earth's surface, it's also not 9.8 meters per second squared. But we got to find little g on Mars, okay? So that's the acceleration we're looking for, okay? It takes 0.725 seconds for a ball to drop 1 meter on Mars. Oh, it's dropped, so we know the initial velocity is going to be 0. So this is actually the exact same calculation you've been doing for a lab earlier when you did all the accelerations. Let's see, d is going to be 1. The initial is going to be 0 meters per second. Forgive my messy handwriting, but I'm dictating at the same time so you can follow along with what I'm saying. That whole term becomes 0 plus 1/2. A is our unknown, and t is going to be 0.725 seconds, and that whole thing is squared. All right, so on the left side here, we have 1, right? And then we have, actually, I'm going to multiply both sides by 2 to get rid of that 1/2 on the right side. So I'm going to get 2 equals a 0.725 squared, right? You can throw that in your calculator, divide both sides by 0.725 squared, and you can get your value for G, all right? So we did this the second day of lab. We plotted our data, all right? I'm not gonna plot that for you, but your data would look something like this, all right? Get a nice quadratic or a nice polynomial, okay? When you put it into sheets, it would look something like this, okay? Let me talk a little bit about this, all right? The equation you have here, all right? So there's a video on how to do this also, but the equation you have here, right here, this is analogous to the d equals v initial times time plus 1/2 at squared. The coefficient of x squared is the same as the coefficient of t squared. So this number here, 4.82, is equal to half of the acceleration. So in my case, 4.82 equals half the acceleration. Okay, so I'm going to kind of skip through this a little bit. 4.82 equals half the acceleration. So the acceleration is, multiply both sides by 2, 9.64 equals the acceleration, meters per second squared. All right, that's a pretty good value, pretty close to that 9.8 accepted value. There is a video for how to do this in Google Sheets, so make sure you check that out. All right, have a great day, and I will see you in class.